Welcome, my fine young cosmonauts, to the last 5 days of the course. Well, 7. I'm going all the way to next Monday. I've been racking my brains as to how to end this course. I like to put a big bow, a giant concluding tie together. But it's really difficult to retailor all the stuff that I would have done in class to make it suitable for online learning with you. I don't want to bog you down in lots of mathematical practice, but again, I've been really trying to push how you can integrate math into your answers in science. Observation and inference, logical reasoning, is an important skill to have as a human being, not as a student. I mean, it's great as a student, but really for a human being. So you can read these two at your leisure. There are only 2 parts to this I'm going to ask you as an assignment, and that's this one right here. I want you to read these questions. Just type your answer in there and there. You're 50% done. Then you're going to look at the seasons on the planets, and you're going to answer this page. Okay? In order to do that, I want you to check out the sun ray simulator on this website. There are dozens of simulators here. If you like astronomy, you might get lost. They're fairly old school, but the sun ray simulator will get you the seasons down. This one is very advanced. Ignore it if you're at all concerned. In your textbook, these are the 2 pages that will cover the seasons. What's missing is there was an entire debate on the nature of the Earth's orbit, and that's where I still haven't figured out if I can include it. It's similar to the Rutherford versus the Thomson plum pudding model of the atom. So I'm focusing on hard skills. So read this. Then you can go in here and answer. There's your online textbook again if you don't have one. Here are the tilts of the planets. So Mercury is oriented vertically, it just spins. One of the common beliefs is that the distance from the sun is the cause of the seasons, not the tilt. Let's take a look at the Earth's orbit scale. I've done this little drawing in CorelDRAW, and I've set up a mock orbit of the Earth around the sun. So I'm going to put the sun like that, smack in the middle. There we go. CorelDRAW is a Canadian program. It's like $500 a lot of times, but you can get it on sale for $100. If you like drawing, it's a great program. I don't work for CorelDRAW nor make any money from them. So here's a mock Earth, 150 millimeters across in its orbit. This is the orbit of the Earth. Okay, it's going. If I click on this, I get a size of 150 by 150 millimeters. Yeah, I know it did it with all these digits, but trust me, if I enter 150 here, it keeps going back to that. So it's got a little bit of a rounding error. This is a perfectly circular orbit. But the Earth goes from 152 to 147. That's the widest and closest it gets. That's it. That's how much different it is from a pure circle. Let's do that again. Pure circle, not pure circle.
And a new guinea pig hide.
If I do this,
for a second, you were just going to say a new guinea.
And then I do that. Can you see the elliptical orbit?
Yes.
Tycho Brahe,
A new light for
an astronomer by eyesight, spotted this difference in the 16 or 1500s. That is how not round the Earth's orbit is. If people would stop talking so loud behind me. But textbooks show the Earth's orbit like this. Why do they show it in elliptical that severely? Because if they showed the ellipse to correct scale like this in the textbook, you would barely see that ellipse. So they exaggerated. But the end result is generations of parents have taught their kids that the Earth is colder in winter because it's farther from the sun, and it's warmer in summer because it's closer to the sun, and the textbook drawings support that evidence. If you read the textbook, you won't get the support, but the diagram is throwing you. There is only one planet on a severely elliptical orbit, and that's Pluto, and even that one, the ellipse is still very close to circular. If you want highly elliptical orbits, we're talking comets. And comet orbits are insane. In terms of elliptical, comet orbits are like that's not even touching it. Some comet orbits almost make it halfway to the nearest star. So all the planets are effectively on round orbits. Now take a look at this from a distance. Now you see what I'm talking about? That is the Earth's orbit, purely round. That is actually to scale how much it's out of round. And that is why textbooks are wrong. When you get really close, I think you can see it. Okay? So this is how diagrams often steer you wrong. How can we prove to you that distance doesn't matter? Because I'm editing this on my own, you can see examples of how I edit my own work when I don't have time to professionally redo them. So never think that as a teacher I don't edit and improve my phrasing. Eventually I'll do a much better version of this where it is all edited out. But sometimes I do these videos 10 to 15 times before I'm happy with it. I don't have time for that now. And at this point, you can completely tune out. This is strictly for the students who want to exercise some more advanced math. When any energy or force travels away from its origin, it spreads out in space and has to cover more area. Like this. This is what causes light to become dimmer as you move away from it, or the warmth of a campfire fades as you back away. It is called the inverse square law and is critical to understanding physics. Using it, we can predict how much colder and colder, brighter and dimmer. What the hell did I write? You can tell, like, I've been scrambling some to be from other planets. Isaac Newton discovered the formula. I don't know if he discovered it. It was like, look what I found under this rock. It's a formula. And he came up with a formula that's really simple. The force, now if it's light, we'd call it the intensity, changes by the inverse square of the distance. What does that mean? If you were a unit of 1 away from a force, you'd have 1 over 1 squared, which is 1. But if you were 2 units away from a force, it would be 1 over 2 squared, which is 1/4. If you were 10 units away from the force, it would change from 1 to 10 squared, or 1/100th. Okay? So we want to take a look at what Newton's law would predict as a surface temperature. And I'm going to do an example with Uranus. Earth is 1 unit away from the sun, 1 astronomical unit. You calculated in your assignment. So 1 over 1 squared is 1. Earth has 100% sunlight. As a multiple, we would call this 1 times, or 1x. Someone gave you a microscope that said, this is 1x magnification. It just don't bother. What about Uranus? If you look up Uranus, astronomical units, it's 19.8. So Uranus is basically 20 times further away from the sun than we are. And the law would predict 1 over 20 squared. 1 over 20 squared. Which is 1 over 400. This means sunlight on Uranus is 1 400th of what it is on Earth, or 400 times less. As a fraction, we can do this, right? You can go 20 squared, and the nice thing on a calculator, you can do this 1 over really easy. I just did the 20 squared part, and then if you look around here, there it is, 1 over, and it'll flip it. So it's decimal 0025. Now, if you got 1 out of 400 on a test, and this is the 1 over 400, how do you turn it to a percent? You just multiply by 100. So the sunlight on Uranus is 0.25% of what it is on Earth. A quarter of 1%. What would that do to the temperature? The temperature on Earth is average 1 degree. All right, you gotta remember, it's an average year-round planet-wide. We have to do this in what's called Kelvin. Kelvin temperature is shifted. 274. 273 is 0 degrees. So 274, we would expect the temperature on Uranus to be 1/400th of that. So I'm going to take 274 divided by the 400 times smaller, and I get a temperature of 0.685 degrees. I'm going to call that 1 Kelvin. I'm going to round it. My prediction is 1 Kelvin. Now, if 0 C is 273 K, then 1 Kelvin is minus 272 Celsius. It's cold. Here's another case of an error I just found. The surface temperature of Earth is 15 degrees, which is 288 Kelvin. It won't change the answer at all. It's within my rounding. But this is where I kind of like the learning at home. It's allowed me to catch mistakes that I didn't know were there and fix them on the spot. Okay, let's take a look at Uranus average temp. Celsius. Minus 224. Where did I go? There we go. Minus 224. That is not bad. $49 Kelvin. Uranus is warmer than we thought. It's warmer than it should be. Now, if you calculated 272 below zero and the answer is 224, a lot of it's still 49 degrees between that. The steps in Kelvin and Celsius are the same, just the 0 point is difference. But for a high school simple calculation, that's not terribly off. That's 50 degrees. Now, 50 degrees off, if you go like, we were going to go hiking in the deserts of Saudi Arabia, and we thought it was 30 degrees, but we were 50 degrees off. And it's like 80 degrees. You're dead. You're dead. You're dead. You're dead. You're dead. But nonetheless, in a calculation that has thousands of possibilities, we came close. But the weird part is, we predict a temperature of 1K and Uranus is 49. It's warmer than it should be according to this law. So what would be unusual about Uranus that makes it a lot warmer than it is? And then we're like, is it the color? Is it gravity? Are there volcanoes? Alien bases. Okay? So when we look at these temperatures, they may not obey the inverse square law, meaning there's something else going on. Otherwise, this law should easily predict what's going on. So there's the one I just did for Uranus. So that's all you have to do for Venus and Mars. Look up distance from Sun in AU. Once you get that distance, square it, flip it upside down, and you will get your answer. Then multiply it by 100 as a percent. And whatever this r squared was, if you get 1 over 400th, you call it 1/400th. If you get 1 over 3, you call it 3 times less. Okay? And then you can predict your average surface temperature, and then you can look it up and see how close you were. You do your average surface temperature by just dividing this number down by the percentage. All right? And then you can read the magnetosphere stuff if you wish. It's optional. It's cool, but it's optional.